Swayam Prabha. Digital India. Educated India.
Welcome to today class of nonlinear vibration. Today we are going to study more on this Foucault theory and also application of this parametrically excited system. So, we will take one example of a pneumatic artificial muscle which can be modeled as a parametrically excited system and we can find the response of the system. Last class we have discussed regarding a parametrically excited system and given some examples. For example, for plucking the fruits in the tree, so you can shake the tree so that the fruits can come down. So, here you are exciting the branch in such way that the application of force and the response are taking in orthogonal direction. In particularly in case of parametrically excited system, we have seen this example, that is a base excited cantilever beam. So, in this base excited cantilever beam, when the base is moving up and down, so we can see the cantilever beam will move in the transverse direction. Here the application of force and the direction of motion are taking place in perpendicular directions. That is a typical case of a parametrically excited system. So, you have seen in parametrically excited system, the force application of force and, for example, so let us take this cantilever beam. So, here the force is applied, let the force is applied in the axial direction and the displacement is taking place in the perpendicular direction. So, here also you can note that this force P is equal to P0 plus P1 cos omega t. So, here we are giving a time varying force. So, in this time varying force, so if you write down the equation of a parametrically excited system, it can be typically written in this form. So, u double dot plus p t u equal to 0. So, this is known as the Hill's equation and in this Hill's equation, so you have already seen. So, if we are writing this p t in this form delta plus 2 epsilon cos omega t into u equal to 0. So, this is known as Matthew equation. So, we know this Hill's equation and Matthew equation. So, if you compare this equation with the system, for example, you take the system, so which is directly excited. So, for example, here you have applied a force, for example, this is P equal to P0 cos omega t. So, this is the force you have given and the system is moving in this transverse direction also. So, here the direction of force and the direction of application, direction of force and the direction of response are in the same direction, but in this case the force is applied in the horizontal direction and the displacement is taking place in the transverse direction. So, this is the difference between this parametrically excited system and the direct force excited system in physical sense. Also, the resonance conditions we have discussed yesterday. So, in this case in direct excitation, when this omega, that is the external frequency, equal to the natural frequency, omega equal to omega n. So, we are getting the resonance condition, but in this case, in case of parametrically excited systems, so we have discussed regarding 3 different type of resonance condition. So, one is known as principal parametric resonance condition, principal parametric resonance condition. So, in this condition, so omega, that is the external frequency, can be retained as twice the natural frequency. So, in this condition, so it is written, it is equal to twice the natural frequency. So, depending on the fast mode, for example, let us take a continuous system like this cantilever beam or a simply supported beam. So, in these cases, so we have infinite number of natural frequency because these are the continuous system. So, in case of continuous system, so we have infinite number of natural frequency, we will have infinite number of parametric resonance condition. For example, it may be at omega equal to 2 omega 1, omega equal to 2 omega 3. So, here omega 1, omega 2, omega 3 are the natural frequency of the system. Also we have discussed or I told, so we can have the resonance condition that is known as combination parametric resonance condition, combination parametric. So, in case of combination parametric resonance condition, we have this omega equal to, that is external frequency will be equal to, external frequency omega will be equal to omega m plus minus omega n. So, this is combination parametric resonance of some type, and another one we can have also omega equal to omega m minus omega n. So, in this case, so it is combination parametric resonance of different type. So, this m and n can take any number, that is 1, 2, 3, 4 depending on the natural frequency of the system. Here, so you have observed that in case of parametrically excited system, the resonance conditions occur away from the natural frequency. It may occur twice of the natural frequency, which is known as principal parametric, or it can occur at a frequency which may be some or different type of different natural frequency. But in case of direct excitation, resonance will occur at a frequency near to the natural frequency of the system. Further we have studied, for example, so we have a system like this Duffing equation. So, the for studying the stability, when we perturb this equation actually yield a equation which is similar to that of a parametrically excited system. Here we have taken u equal to u0 plus u1, u is the equilibrium solution. So, taking this equilibrium solution, so by substituting it in this original equation, so we got this u 1 double dot plus omega 0 square u1 plus 2 epsilon mu u1 dot plus epsilon f t u1 equal to 0. In this parametrically excited system, so you have seen the coefficient of the response, here response is u1. So, the coefficient of response is a parameter which is periodic in nature. So, this f t is a periodic function. So, if the coefficient of u, that is the response, is a periodic function, then we call these type of equations are parametrically excited system, equation for a parametrically excited system. So, here we have applied, last class we have seen how to apply this Foucault theory. So, in case of Foucault theory, we have studied that for a second order differential equation, so we can have two fundamental sets of solution. For example, let us take two fundamental set of solution, that is u1 t, u2 t. So, the combination of this fundamental solution is also a solution, that thing we know. So, from that thing we have proceed and we have found that if we can find the roots of the monodromy matrix, if it is within the unit circle, so it must be within the unit circle. So, if it is within the unit circle, then it is stable. So, if it is outside the unit circle, then it is unstable. So, how to do that thing? So, we have taken, for example, in this case, so for solving this equation, this u1 double dot plus p1 t u dot plus p2 t u equal to 0. So, we initially assume two solution u1 t and u2 t. So, we have seen that u1 t plus t is also periodic, and that thing can be written as in this form. So, u1 t1 plus t can be written as a11 u1 t plus a12 u2 t. Similarly, u2 t plus t can be written as a21 u1 t plus a22 u2 t, and so that you can write a matrix. So, this u1 t plus t and u2 t plus t. So, we can write a matrix actually with a matrix, so which is equal to a into u1 t and u2t. So, this way we can write a matrix, and by finding this eigenvalue of this matrix, so we can tell whether the system is stable or not. So, by finding the eigenvalue of that matrix, if the roots or the eigenvalues are within this limit cycle, unit cycle, then it will be stable. So, if it is outside this unit circle, then it is unstable. So, this is the real part and this is the imaginary part. So, this way we have studied this fluid theory. So, corresponding, if lambda I greater than 1, we can find, if lambda I greater than 1, then gamma I is also positive. So, either we can find the roots lambda I to study the stability, otherwise we can find this fluid multiplier gamma I also to find whether the system is stable or not. So, if gamma I is positive, then we know that the system is unstable, and if gamma I is negative, then we can tell the system is stable, and the relation between lambda I and gamma I is this. So, gamma I equal to 1 by t ln lambda I. So, either you find this gamma I or lambda I and you can find the solution. So, to find this gamma I, so you may initially take a solution in this form, in the form of phi. That means, V1t if you take equal to the solution in this form, e to the power gamma 1 t phi 1 t, and V2t equal to e to the power gamma 2 t phi 2 t. So, where phi I t plus t equal to phi I t, then directly you can get gamma. So, instead of getting lambda, so if you get gamma, so in case of those are fluid multipliers. So, knowing this fluid multiplier, you can tell whether the system is stable or unstable. So, last class we have seen one example. So, let us see another example. For example, let us study the stability of Hill's equation by taking this initial condition u1 equal to 1, u1 dot equal to u1 dot 0 equal to 0, u2 equal to 0 and u2 dot equal to 1. Like previous class, here also we can take this u1 t plus t equal to a11 u1 t plus a12 u2 t. Similarly, u2 t plus t equal to a21 u1 t plus a22 u2 t. Similarly, u1 dot t plus t equal to a11 u1 t plus a12 u2 dot t, and u2 dot t plus t equal to a21 u1 t plus a22 u2 dot t. By substituting these initial conditions, so we can find this a11, a12, a21, a22, where it can be written a11 can be found as u1 t, a21 can be found as u2 t. So, you just see, first you substitute this in this equation. So, t equal to 0. So, u1 0 plus t, that is u1 t. So, u1 t is nothing but a11 into u1 t equal to 1. So, this becomes a11. So, you got a11 equal to u1 t. Similarly, a21, to find a21. So, you just see this equation, second equation here by substituting t equal to 0. So, u2 t equal to a21 into 1, that is a21 plus a22 into u2 t, as u2 t equal to 0 you have taken. So, this a21 becomes u2 t. Similarly, from these two equations also we can get a12 equal to. So, you just see here you are getting u1 t plus t equal to a11 u1 only. Similarly, uncoupled. So, now you are not getting the coupled term, because this here this a u2 or you are taking this initial condition, and from this initial condition. So, 1 term becoming 0. So, directly you are getting the coefficients. In third case also you got the directly you got the coefficient a12 equal to a u1 dot t, and a22 similarly you got equal to u2 dot t. So, this A matrix now can be reconstructed equal to u1 t, u1 dot t, u2 t, u2 dot t. We can find the determinant of this A minus lambda I equation. So, to find the eigenvalue, so either you directly find the eigenvalue or you just find the determinant of this thing and equate to 0, or this is a 2 degree of 2:2 matrix, then easily you can do it by hand. That is why simply you can find this determinant of a minus lambda equal to 0. So, which will give rise to this equation, that is lambda square minus 2 alpha lambda plus delta equal to 0. So, where alpha equal to half of the trace u 1 plus u 2 dot, and then so half of u 1 plus u 2 dot, because we are taking 2, otherwise you can write this lambda square minus the trace into lambda plus delta equal to 0. So, where delta equal to u 1 t into u 2 dot d minus, this is the determinant of a u 1 t into u 2 dot t minus u 1 dot t minus u 2 t. After getting this alpha and lambda, so you can write down this thing. So, you can find this lambda square. So, from this thing you can find the root. So, the roots are lambda 1 2 equal to. So, you can use this formula minus b plus minus root over b square minus 4 a c by 2 a, and you can find this lambda 1 2 equal to alpha plus minus root over alpha square minus 1. So, from this thing you can note this lambda 1 and lambda 2. So, if you multiply these 2, then this becomes, you just see this is alpha. So, a square minus b square. So, it will be, so let alpha equal to a and this part is b. So, this is a plus b into a minus b. So, a plus b into a minus b is a square minus b square. So, your lambda 1 into lambda 2 equal to a square plus b square. In case of b square, it is equal to alpha square minus 1 only, a square minus b square. So, it is a square minus b square. So, this becomes alpha square minus alpha square plus 1. So, this cancels and this becomes 1. So, here you have observed that this lambda 1 into lambda 2 is always equal to 1. So, if one of the root is less than 1, so for example, let lambda 1 equal to half, then lambda 2 must be equal to 2. If one of the root is greater than 1, so the other root must be equal less than 1. So, in that case, one of the root is lying outside the unit circle, as lambda 1 and lambda 2 for a stable system must stay within the unit circle. So, that is why to have a stable system, this lambda 1 and lambda 2 either must be equal to 1 or minus 1. So, if it is 1, then we can have the transition curve. So, from here, so you can observe that we have 3 conditions from this lambda 1 and lambda 2. So, you observe lambda 1 equal to alpha plus minus root over alpha square minus 1. So, from this thing, so we can observe that if alpha is greater than 1, so you just see this equation, that is alpha plus minus root over alpha square minus 1. So, if alpha is greater than 1, then this alpha square minus 1 is positive. So, we have a positive root here, then this alpha plus this positive part will be greater than 1, and then that minus part will leads to less than 1. So, that means if alpha is greater than 1, so we have a unstable solution. The solution will be unbounded as one of the lambda is greater than 1. Let us see if alpha is less than 1. So, let us take a number where alpha is less than 1. So, if it is less than 1, so this part, this alpha square minus 1 is negative. So, we have a imaginary term here. So, we have a complex number here, complex conjugate. So, if alpha is less than 1, so we will have a complex conjugate term. So, if we have a complex conjugate term alpha less than 1, so we have a complex conjugate roots, but the absolute value is less than 1. So, here the absolute value will be less than 1. So, it will lie inside the unit circle. So, the system will be stable or the periodic solution will be stable, but if alpha equal to 1, then this root over alpha square minus 1 equal to 0. So, we have 2 real root. So, alpha, if alpha equal to 1, so we have 2 real root, that is and equal root. So, that is lambda 1 equal to lambda 2 equal to either it may be, so it can be 1 or minus 1. We have a transition curve, periodic solution of period t when lambda 1 equal to lambda 2, lambda 1 equal to lambda 2 equal to 1. Similarly, periodic solution of period 2t when lambda 1 equal to lambda 2 equal to minus 1. So, you just see in both the cases, so the product is lambda 1 into lambda 2 equal to 1. Here also minus 1 into minus 1 also 1. So, when it is minus 1, so previously we have seen that it must be of period 2t. So, this way we can study any given any system, given any periodic solution. So, we can study whether the solution is stable or not. You can recall in case of a fixed point response. So, generally we find the Jacobian matrix and the eigenvalues of Jacobian matrix, but in this case we are taking another matrix, that A matrix, which is generally known as the monodromy matrix. So, here we are finding the eigenvalue of the monodromy matrix, but in case of the fixed point response we used to find the eigenvalue of the Jacobian matrix. This difference you must clearly understand. So, let us take in the case of the Matthew equation. So, in this case you just note that here this equation can be written in this form, Matthew equation. So, that P t we are replacing it by delta plus 2 epsilon cos 2 t u. So, taking this initial condition u 1 and u 2. So, after one cycle we can find what is the response. So, after finding the response for two initial condition, for example, let us take u 1 equal to, starting with u 1 equal to 1 and u 1 dot equal to 0. So, we can find what is u 1 t and u 1 dot t we can find. Similarly, starting from u 2 equal to 0 and u 2 dot equal to 1. So, we can find what is u 2 t and u 2, this is u 2 dot. So, u 2 dot t. So, after finding these 4 parameters, so this thing we can get it from by solving this equation. So, this equation we can use this Runge-Kutta method to write in. So, we can write this equation into first order differential equation, and after writing this as first order differential equation. So, by taking this initial condition u 1 equal to 0 and u 1 dot equal to 0. So, you can find this the solution after one cycle. Similarly, by taking this initial condition 0 and 1, that is u 2 equal to 0 and u 2 dot equal to 1. So, we can get u 2 after one cycle, that is u 2 t and u 2 dot t. So, you just note here that this, now we can construct this A matrix. So, now constructing this A matrix, we can note that this A matrix is a function of this delta and epsilon. So, delta and epsilon. Now, by taking this omega equal to root over delta. So, we can plot this omega and epsilon. So, we can plot this omega and epsilon and find the value of alpha for which alpha equal to 1. We can find the value of alpha for which this is equal to 1. So, if one can plot this thing, that is epsilon versus this is epsilon versus this omega, epsilon versus omega, then one can get a curve like this, where this part is stable and this part is unstable and again this is stable. So, this is known as the instability region, or this is otherwise known as parametric instability region, parametric instability region. So, on the transition curve, the response is periodic. So, outside this thing, this is stable, this is unstable region, and again this S is the stable region. So, this way one can physically study any given equation. So, whether it is Matthew equation or any other given equation. So, first find, so if it is periodic, so then you can find this way. So, here you just note this cos 2 t, you just see at omega equal to 2. So, at epsilon equal to 0. So, omega equal to 2. So, the instability region start from this position 2. So, here this delta you can see. So, that when omega equal to 2, so you can get this curve. So, for any value of epsilon, you can take any value of epsilon and you can see, or you can find the solution and check whether the solution is stable or not by solving this equation by using Runge-Kutta method. Okay, or you can use any perturbation method to solve this equation and study that thing. So, let us see another method to solve this or to find the instability region in case of Matthew equation. So, here we can use this Hill's determinant, Hill's infinity determinant method to find the stability conditions in case of the Matthew equation. So, this is the Matthew equation. So, now we know by using this Floquet theory we can write this u equal to e to the power gamma t into phi t. This phi t also we know that this phi t is periodic, that is phi t equal to phi t plus t. So, as this is a periodic function, so we can expand this phi t by using a Fourier series. So, let us use a Fourier series to expand this phi t. So, that thing can be written as phi n e to the power 2 I n t, where I equal to root over minus 1. Now, this is n equal to 1 to infinite, you can take, or n equal to minus infinity to n equal to minus infinity to plus infinity, n equal to minus infinite to plus infinite. So, you are taking e to the power 2 I n t. So, for n equal to 1, so you have this phi 1 e to the power 2 I t. Similarly, n equal to 2, you have 4 I t. So, that way you can go on expanding. So, put different value of n and you can find. So, as it is from minus infinity to infinite, so you can have large number of exponential function. Now, by substituting this equation, so you just see e to the power gamma t and we have expanded this phi t in terms of its Fourier series. Then we can write this thing equal to n equal to minus infinite to infinite phi n e to the power gamma. So, you can e to the power gamma t into e to the power 2 I n t, it will be equal to e to the power gamma plus 2 I n into t. Now, by substituting this u in this equation, so if you differentiate it twice, now you can differentiate it twice. So, this becomes, this is gamma. So, this term will come out. So, this is gamma plus 2 I n, gamma plus 2 I n. So, twice you are differentiating. So, it will be gamma plus 2 I n whole square into the same term will be there. So, now you just substitute it in this original equation. So, you got this one. So, it is minus n equal to minus infinite to infinite summation n equal to minus infinite to infinite. So, this is the term square term due to differentiation. So, gamma plus 2 I n whole square plus another term is there delta u n. So, as you have this delta u term, so delta into u, so you have delta into u. So, from that thing also you can get one term, that term also you can take it. So, then this becomes gamma plus 2 I n whole square plus delta into phi n e to the power gamma plus 2 I n t. So, plus then for the other term, so for the other term you just see the other term is 2 epsilon cos 2 t into u, 2 epsilon cos 2 t into u. So, this cos 2 t you can write in exponential form also, and then you can multiply that thing with u n. So, the resulting things will be, so you know cos phi you can write, or cos theta you can write equal to, cos theta equal to e to the power I theta plus e to the power minus I theta by 2. So, by putting this thing, so we have a 2 term there, 2 cos theta or 2 cos omega t. So, 2 will cancel. So, you will have this e to the power I theta plus e to the power minus I theta. Here theta is nothing but your gamma plus theta will be equal to. So, in this case, so this is cos 2 t you are taking. So, you are taking cos 2 t. So, it will be, we have taken cos 2 t. So, then it will be e to the power I into 2 t plus e to minus I into 2 t divided by 2. This is cos 2 cos. So, we have 2 cos, we have a term 2 epsilon cos 2 t. So, 2 epsilon cos 2 t will be, so 2 will cancel. So, it becomes epsilon e to the power 2 t I into 2 t plus e to the power minus I 2 t. So, now we can multiply this phi, which is summation of n equal to minus infinite to infinite e to the power 2 I n t. So, if we multiply this with this term, so then the resulting things will be this. So, in one case it is added by, so this term, so that is gamma t is there in addition to in terms of 2. So, this is 2 will be added. So, if you take these 2 common, so this becomes 2 I n plus 1 t, another term. So, for this 2 I t, so this is the n plus 1 term you got, and for this minus 2 I t, so by taking these 2 common, so this becomes minus 2 I n minus 1 t. So, you just see, so we have a term e to the power gamma plus 2 I n t, we have another term 2 I n plus 1 t, and here another term, so that is 2 I n minus 1 t. So, now we can equate the terms coefficient of exponential function to be 0. So, now we can take different exponential function and equate it to 0. For example, by taking n equal to 1, so we will have gamma plus 2 I here. So, similarly here you just see this is a term n plus 1 and here is a term n minus 1. We have to take a lower term here to have the same exponential form. So, if we are taking the, for example, mth term here, so m, so in that case it will be m minus, if you will take n equal to m minus 1, then this becomes m. This is m minus 1 plus 1, so this becomes m. Similarly, here we have to take n equal to m plus 1, so that this will also give rise to m. So, this way we have to choose the proper number to find the exponential function to collect the coefficient. So, because this is a infinite, so you just see n equal to minus infinite to infinite. So, we can get or we can collect a infinite determinant from this equation. So, to write down this equation, and from this equation if we collect the coefficients of exponential function, we will have a infinite number of equations. So, the nth equation can be written in this form. You just see the coefficient of nth equation can be written in this form, that is gamma plus 2 I n square plus delta. So, this is the term gamma plus 2 I n square plus delta into phi n. So, you just see everywhere this e to the power gamma plus 2 I n t can be taken common, and so it can be taken out this side to have this e to the power gamma plus 2 I n. So, here n must be, so we have to take n minus 1. So, if it is n minus 1, so then n minus 1 plus 1 will be n. So, that is why it will be epsilon into phi n minus 1. Similarly, for this one we will get only one term, that is n, we have to replace it by n plus 1. So, that is why this becomes phi n plus 1. So, this is gamma plus 2 I n whole square plus delta into phi n plus epsilon into phi n minus 1 plus phi n plus 1 into e to the power gamma 2 I n t equal to 0, as exponential function cannot be 0. So, this must be equal to 0. So, we can find this must be equal to 0. Now, from this equation, so we can, for a non-trivial solution, so when the solution is non-trivial, that is non-zero, the determinant of the coefficient matrix must vanish, since the determinant is infinite. So, here we have infinite number of equations. So, that is why we have this infinite determinant. So, since the determinant is infinite, one may divide the mth row by delta minus 4 m square for convergence consideration to obtain the following Hill's determinant. So, we can get this Hill's determinant actually by dividing by, so by dividing by delta minus 4 m square. So, by taking m equal to, for example, m equal to 1, this is delta minus 4. So, m equal to 1 we can take. So, this becomes epsilon by delta minus 4 square. So, then delta plus gamma minus 4 I whole square by delta minus 4 square. So, other terms will be 0. Similarly, we can get all these equations. So, from the original, the equation what we have derived here. So, from this equation we can find all these terms. The determinant can be rewritten as delta gamma equal to delta 0 minus sin square half I pi gamma by sin square half pi root over delta. So, from this thing, since the characteristic exponent of the solution delta gamma equal to 0. So, from this thing we can find this gamma. So, gamma equal to, gamma is Foucault multiplier. So, this gamma equal to plus minus 2 I by pi sin inverse delta 0 sin square half pi root over 6 to the power half. So, from this thing, so you know, so when gamma is positive the system is unstable, and when gamma is negative the system is stable. So, you have to find the value of gamma for which it is 0. So, first to find the transition curve, or you can find the lambda value. So, if the lambda is laying in the unit circle, then it will be stable. So, you can also further you can consider only the central 3 rows and 3 columns. So, from these things, so you can consider the central 3 rows. So, 3 rows and 3 columns you can consider, and from that thing also you can write these 3 equation, that is delta plus gamma minus 2 I square epsilon 0 epsilon delta plus gamma square epsilon, then 0 epsilon delta plus gamma plus 2 I whole square and make it equal to 0. So, from this thing finding this determinant. So, this is the determinant. From this determinant you can find the, or you can plot this delta versus either delta versus epsilon or omega versus epsilon, where omega is root over delta. So, you can plot this omega versus epsilon to find the instability region. So, you just see when gamma equal to 0, then you can get the transition curve. So, from this thing, so you got the condition that delta equal to minus half epsilon square or delta equal to 4 plus half epsilon square. When gamma equal to plus minus I, transition curve you can give it like this, that is delta equal to 1 plus epsilon and delta equal to 9 plus 1 by 8 epsilon square. So, you can plot this delta versus epsilon and can get the transition curves. So, this is as an assignment. So, you can plot this delta, either delta versus epsilon or this omega versus epsilon curve to find the transition curve. So, let us take one example. For example, we are going to take a parametrically excited pneumatic artificial muscle, and here we will study the response of the system which is similar to that of a parametrically excited one. So, why this becomes parametrically excited also we will see. So, before that thing you must know what is artificial muscle. So, these are the different artificial muscles have been shown. So, various type of pumps. So, the first one, so this one is known as Mickey vein muscle or braided muscle. So, then this is pleated muscle, then this one is palm reinforced with Kevlar fiber. So, fiber is embedded in this thing. So, then you can have the earlot netted muscle, this one earlot netted muscle, then pointer hyperboloid muscles is there, then you can have, this is hyperboloid muscle, you can see this hyperbolic thing. Then we have this Romac muscle. So, there are several different pneumatic artificial muscles are there. So, here you are inserting this air pressure, and due to air pressure, so as the length is constrained, so it cannot go beyond a certain length. So, then it will bulge. So, as it is bulging, then there will be contraction in this muscle. So, due to this contraction, so it can pull to do some work. So, that way you can use it for a different purpose. So, this is the L max, this is the L intermediate, and this is the L minimum. So, this force equal to 0. So, you have a intermediate force here, then here is the maximum force you are applying. So, this is for a general palm. In this way you can do the study. So, there are several literature available on this pneumatic artificial muscle. So, some of the literature are given here. So, for example, this Chow et al. So, use this Mickey vein muscle which is developed by a physician Joseph L. Mickey vein in 1950 for polio patient rehabilitation purpose. So, that is a cylindrical braided muscle that has both its tube and its sleeving connected at both ends to fittings. This material used are latex and silicon rubber and nylon fiber. Then Nakamura et al. So, long lived because it does not require a sleeve and can express an allotropic property due to the way the fiber is knit into the tube. Material used are high intensity glass fiber and natural rubber latex. Then diadenatal, they inflate without material stretching and friction. So, no stress in the direction perpendicular to the axis of symmetry, contraction forces and maximum displacement are very high. This Valle et al. So, provide the high force and compliance of McEwen pneumatic artificial muscle with low threshold pressure. So, made up of non-viscoelastic material with high tensile and low bending stiffness. So, there are many literature available. At the end I will show a reference, from that thing you can know what are the papers available in this field. So, some of the papers have been written here. This is the McEwen type of muscle. So, you can see the photograph of the McEwen type. So, this is the Festo McEwen type of palm. Palm is pneumatic artificial muscle or pneumatically actuated muscles also. So, you can put palms reinforced by straight glass fiber. So, here it is this glass fiber you can see. So, there are several rings are also there. So, this is a rubber tube. So, rubber tube with this glass fiber embedded in this. Then you have the terminal from where you can use these pipes for this pneumatic supplying this air. So, there are several other related palm photographs also you can find. So, this is piano muscle. Piano fluidic muscle has capacitive strain sensor and a pressure sensor to aid force estimation. So, you can put a pressure sensor and you can put a force sensor also. So, there are several other muscles available. So, some of them have been listed here. For example, this is Yarlot muscle, Romac muscle, Kukoji muscle and Morin muscle, then Baldwin muscle, Painter hyperbolic muscle. So, there are several different muscles are available, and these muscles you can see they are particularly used for this exoskeleton type of thing. So, here this figure of a nurse robot suit. So, she has put a robot suit, so which is pneumatically actuated. This is also power assist wear by D. Sakasi. So, these references I will give at the end of the presentation or this lecture. So, we have multi joint exoskeleton. So, these are the exoskeleton system where you can use this type of muscles, and it can be single joint, multi joint. Here we are proposing one artificial muscle. Actually, this work is the PhD work of my PhD student Mr. Bhavan Kalita. So, here we have developed one artificial muscle by using this Muga silk and part silk. The muscle what we are showing here. So, the maximum length of the palm is 450 mm. So, inner diameter is 12 mm, maximum outer diameter is 22 mm. So, thickness of the palm is 2 mm to 5 mm. So, maximum number of linear for fabric reinforcement, 25 fabrics have been put here. You can fabricate this thing by using the silicon rubber, and then so this is the fabricated muscle. So, these are the fabricated. So, this is the Muga silk or part silk. So, we have made one mold. So, in this mold we have fabricated this muscle, and we have characterized these muscles also to find the property. So, here you can see we can use this muscle. So, for example, this is the muscle, let us use this thing for the analysis. So, here we put a spring, one side a spring and other side spring and damper and other side this muscle. So, this is the pressurized end, inlet and outlet. So, you will have inlet and outlet. So, this is the mass, it is hanging. So, this is a single degree of freedom system. So, if you remove this artificial muscle, so this is a spring mass damper system only, but now by putting this artificial muscle here, so and putting this air, so we will see how the equation of motion will change. So, if you draw the free body diagram of this one, so it will be subjected to mg force downward, that is the weight, then we have a spring force k x plus delta, then we have the mx double dot, that is the inertia force, and in addition to that we have this muscle force F. So, this muscle force is a function of the displacement x and pressure P. This way we can write, now we can write the equation of motion of the system. So, you just see mx double dot plus kx plus ex dot plus F muscle minus mg equal to 0. So, we have to take this F muscle in this form. So, it is followed from the work of Hong Bing et al. So, F muscle x bar P equal to C1 plus C2P plus C3P square into x bar by L plus D1 plus D2P. So, here a 5 parameter muscle model has been considered here. So, the C1, C2, C3, D1, D2 actually can be obtained from the experiment and performing direct experiment. So, you can get all these system parameter, then you can write this x F muscle equal to in this form. Now, substituting this F muscle in this equation. So, we can write this equation x double dot plus k by m plus C1 plus C2P plus C3P square by m L max x into C by m x dot plus D1 plus D2P by m minus g equal to 0. Now, let us assume that the P, that force, that pressure what you are supplying is in this form, that is Pm plus P0 cos omega bar t. So, that is periodically varying pressure. So, if it is periodically varying with time, then we can write down this equation in this form. So, here you just see in this equation. So, we can, this is dividing by this m. So, this part is the square of the natural frequency omega n square. So, this part will, so if we will write this equation in this form, for example, x double dot plus omega n square x plus 2 zeta omega n x dot plus some term equal to 0. So, in that case this omega n square will be this, and you just see out of this thing, this P is a constant term and P also contain a periodic term. So, as P equal to Pm plus P0 sin omega t. So, here, so by taking this constant term we will have one constant coefficient of x. So, that will contribute for the natural frequency, and another part which will be a periodic function. So, that will be responsible for the parametric excitation of the system. So, by using the parameter omega equal to omega bar by omega 0, mu equal to c by 2 epsilon m omega 0, P1 equal to C2 P0 plus 2 C3 P0 Pm by epsilon m omega 0 square L max, and P2 equal to minus C3 P0 square by 2 epsilon m omega 0 square L max, and F1 equal to, so D2 Pm plus D1 minus mg by epsilon m omega 0 square, and F2 equal to D2 P0 by epsilon m omega 0 square. So, we can write down this equation in this form. So, you just see now this equation, complicated equation is reduced to a simplified form which equal to x double dot plus x plus 2 epsilon omega x dot plus epsilon into, so this is epsilon, so plus epsilon into P1 sin omega t plus P2 cos 2 omega t or tau. So, here the time is written in terms of tau, tau is the non-dimensional time. So, you can observe this non-dimensional time is written in this form, that is you can take this tau equal to omega 0 t, tau equal to omega 0 t. So, t the time in seconds, omega 0, so it is radian per second. So, second cancel, so this tau becomes non-dimensional. So, you can take a non-dimensional time tau equal to omega 0 t. Taking that non-dimensional time, so we can write this equation, that is why. So, x double dot plus omega n square x. So, you just see you have a term, let me take only these two term, x double dot plus omega 0 square x. So, here we are taking tau equal to omega 0 t. So, the differentiation d square by dt square will be nothing but omega 0 square d square by d tau square. So, it will be omega 0 square, let me write it again. So, it will be equal to omega 0 square into d square by d tau square. So, you have a omega 0 square term in the beginning, then plus omega, so this thing will be then written as omega 0 square d square x by d tau square plus omega 0 square x omega 0 square x. Now, you can take this omega 0 square common and divide it everywhere. So, it is divided everywhere, that is why in all the coefficients. So, you can see a term of omega 0 square in the denominator. So, from that way, so you can find this equation. So, here you just note this equation, that is x double dot plus x plus 2 epsilon mu x dot plus epsilon p 1 sin omega t plus p 2 cos 2 omega t into x. The coefficient of x is time varying term, that is similar to p t. So, we have seen, so this can be reduced to that of a Matthew-Hill type of equation. But in the right hand side, so you just see the difference between the Matthew equation or Hill's equation what we have studied, and in the right hand side it was 0, but in this present case in the right hand side we have a term epsilon f 1 plus f 2 sin omega t. So, this is direct excitation term and this is parametrically excited system. So, the system is both parametrically and subjected to both parametric and direct excitation, and you just see the frequency also. So, this is here omega sin omega t, here the term is cos 2 omega t, and here we have a term with sin omega t. So, we have multi frequency excitation. So, here the excitation one is omega and another one is 2 omega. So, we have two frequency excitation in this case. A force vibration system having sinusoidally varying force can be noted in the right hand side also, and the solution is studied by. So, let us use this first order method of multiple scale to study this equation. Here you just see as it is forced and parametric, both the things are there. So, we can study two different case. So, first case is the simple resonance condition. So, we can have a simple resonance condition and we can have parametric resonance condition. So, we have case 1 and case 2. So, in case 1, so we have simple resonance condition. So, when omega equal to 1 plus epsilon sigma, 1 plus epsilon sigma. So, here you just see omega 0 equal to 1, that is why it is written 1 plus epsilon sigma, otherwise you can put this omega equal to omega 0 plus epsilon sigma also. So, in this particular case omega 0 equal to 1. So, that is why it is written that the coefficient this omega 0. So, that is the coefficient of x, that is not the omega 0 term what we have written there. So, this is the coefficient of x, term. So, that is 1 in the non-dimensional form. This is the non-dimensional natural frequency, that is equal to 1. So, that is why we can write this omega equal to 1 plus epsilon sigma, and in the second case we can write the principal parametric resonance condition. So, principal parametric resonance conditions occur when it is equal to twice the natural frequency. Let me write it omega to avoid your confusion. So, twice 2 omega plus epsilon sigma. So, here it is twice the natural frequency, and by using twice the natural frequency we can write this omega equal to 2 plus epsilon sigma. So, now we can get the reduced equation by using this method of multiple scale. So, you can follow the standard procedure of method of multiple scale by assuming this u equal to or u or x we have written. You just see this equation is written in terms of x. So, you can assume the solution to be, so x equal to x 0 plus epsilon x 1, and using different time scale tau n equal to epsilon to the power n t. So, here we are writing in terms of tau, epsilon to the power n tau, and following the procedure, similar procedure. So, we can get two reduced equation. So, these are the reduced equation we got. So, dA by dt equal to this and d gamma by dt equal to this. So, from this thing, so we can find the solution, that is A and gamma. Okay. In this case, this x tau can be written as A t 1 cos omega t 0 minus gamma t 1 plus epsilon f 1 minus p 1 a t by 2 into 1 minus omega whole square sin gamma t 1 plus epsilon into p 1 a t 1 by 2 into 1 minus 1 plus omega whole squares sin 2 omega t0 minus gamma t1 minus p1 p2 a t1 by 2 into 1 minus 1 plus 2 omega 0 square cos 3 omega t0 gamma minus 1. So, you just see, so it contain the frequency, for example, omega t0, here we have 2 omega t0 and another term, that is 3 omega t0. The solution contain 3 frequency here. So, this way you can find the response of the system, and by plotting this response you can check the response of a pneumatically artificial muscle. This artificial muscle is a function of this muscle parameter. So, muscle parameter are written in terms of this F1, F2, F3 muscle parameter, that is C1, C2, C3, D1, D2, and also the pressure. By changing this pressure, so actively you can control the motion of the actuator. So, this thing can be used as a actuator, and you can control the motion by actively changing this pressure. But if you want to change the muscle itself, also you can control by changing this muscle itself, by changing the C1, C2, C3 and D1, D4. That means by changing this muscle, you mean that the length of the muscle can be changed, the thickness of the muscle can be changed, the number of strings you are putting inside this muscle, or the number of strains you are putting inside the muscle has to be changed. So, in that way, by changing this muscle parameter, that means by constructing another muscle, so you can have different type of response of the system. So, in case of principal parametric resonance conditions also, so by using this method of multiple scale, you can have this reduced equation, and from this reduced equation, so you can find the solution in this form. So, this is the solution in case of the principal parametric resonance condition and in case of combination parametric resonance condition. So, you have already seen the response will be different, and you can see the. So, for example, these are the numerical value we have taken for our analysis, and we have plotted the simple resonance condition. So, numerical and analytical solutions you can plot. So, that means numerical solution, that is by using ODE for 5, the original equation you can solve, and then by using method of multiple scale you can get. So, you just see, you can note the response is 5 into 10 to the power minus 3. So, very small. So, that means though it is exaggerated, in actual physical sense the difference is not much. So, the numerical solution and this solution obtained by this method of multiple scale are very close. So, you can see here. So, this is in meter it is written. So, if you convert in mm, so they are in the decimal, difference is in decimal term. Similarly, in case of principal parametric resonance conditions, you can study the responses. So, for different system parameters, so you can compare the simple resonance and parametric resonance condition, and in case of simple resonance, so this is the response curve what you can get. So, here at P point you have a, so you just see this P point you have a saddle node bifurcation, because the tangent at the tangent you just see the tangent is same, and here, so this is a saddle node bifurcation. From a stable branch it is going to an unstable branch. So, if you lower the frequency, so that is sigma is the detuning parameter. So, you can observe that from this point P, so it will jump to point Q. So, you will have a jump of phenomena if you reduce the pressure. So, when you are reducing the frequency of the system, that means by changing your pressure also you can change the frequency. So, that time you can see there is a jump of phenomena, but initially by increasing the frequency, so you can go on increasing the response amplitude. So, depending on the required amplitude, so you can set your frequency and you can get the required length of the or required deflection of the artificial muscle. So, you just see, as you have a number of solution, for example, let us take this. So, you have 3 stable states. So, this you just see the 0 line is also a solution and it is stable also. So, this 0 line as it is a solution. So, you have 3 stable solution. So, this is a tri-stable system and with one unstable response. So 3 stable and 1 unstable, and beforehand before, so for example at this position, so for sigma less than this A value, so you have only one solution. So if you draw the basin of attraction, so you can see you have one solution here, and in the other case you have 4 solutions. So here 1, 2, 3 and this point is the unstable point. So this is the unstable point, so in or saddle point. So in addition to this you have, so this is the trivial state you got. So similar to this, here is the trivial state and another 2 non-trivial state. So this way, by studying the basin of attraction, so you can check the feasibility of the solution, or for what initial conditions you are getting, what response you can study. In case of the principal parametric resonance condition, so you just see the bifurcation is different. So here you have a, so here you have pitchfork type of bifurcation. So here the up to -2 to A, so the trivial state is stable. So only you have a trivial state, that means before A, so whatever may be the force or the frequency, the system is stable. That means it will be in its trivial state, that will be, there will be no inflation. So there will be no expansion of the artificial muscle. So only the artificial muscle will work in this range of A to B. The artificial muscle will work in the range of A to B. From O to A or 0 to A, it will not work. It will work only from A to B, and after B also it may work, but after B it has 2 states. So one trivial state and one non-trivial state. So that thing clearly you can see from the basin of attraction. So at 2 points the basin of attraction have been plotted. For example, at this point, so basin of attraction is plotted here and one is here. So 2 point basin of attractions have been plotted. So in one case you have the saddle point, so you can observe the saddle point. So this is unstable and one stable. So here 2 stable, bistable and one unstable region is there. So based on that thing, so you just see these are the unstable point. So this is the saddle point, so 2 stable point. So that way you can study from the basin of attraction. So in this way, so you have observed that in case of a artificial muscle, so you can have both the simple resonance condition and parametric resonance condition, and by using this method of multiple scale we have seen how the response will behave. I have shown you the basin of attraction. So this basin of attraction you can plot by taking different initial conditions. So later I will tell how to plot these basin of attractions also. So there are many references what I have shown you. So these are the references. Actually a part of this work was presented in this Bitomac conference in 2018. So these are the references. You can study these references, some of these references for artificial muscle. So next class we will study another example. So where we will take a continuous system. So here we have taken a single degree of freedom system, but later we will take a continuous system. In that continuous system, so we will study how by using different methods, so we can get these resonance conditions, the parametric instability region, and we can study also how it can find many applications. For example, one such application I will tell, that is used in this energy harvester purpose. So thank you very much.